Swayam Prabha. Digital India. Educated India.
So, today we will be taking one more example on seepage. So, that is problem 15. The problem says that two rows of sheet piles are driven to a depth of 4.4 meter below the bed of a river to form a cofferdam. Okay. So, excavation is then carried out within the cofferdam up to a depth of 3.3 meter below water level by keeping the area free from water by pumping. The river bed is sand with K, that is coefficient of permeability, is equal to 3 into 10 to the minus 3 centimeter per second and is underlain by an impermeable stratum at a depth of 6 meter below the river bed. What is the quantity of flow into the cofferdam per hour per meter length of the sheet pile walls? The flow net is as shown. So, flow net is shown there. So, if you look at the flow net, so first let's understand the problem. So, you have a row of sheet pile. So, this is one row of sheet pile, this is another row of sheet pile which goes parallel. Okay. So, these two sheet piles go parallelly and within that zone basically you want to excavate. So, this is within that zone you want to excavate. Okay. So, and you need to find out the flow, seepage flow rather, and you need to find out that how much or what should be the rate of pumping, so that you will be having some dry working condition inside the cofferdam. So, these two sheet piles, I mean row of sheet piles will make the cofferdam, will construct the cofferdam, and inside the cofferdam then you will pump the water, so that you will be having some dry working condition and you will be excavating the soil from the cofferdam. So, now you have water level on both the sides, right. So, 1.8 meter height of water, okay, on the other side of the sheet pile, and the depth of permeable stratum. So, that is 5 meter. Okay. After that you have the impermeable stratum, and basically if you consider this problem is very symmetric problem, right. So, if you consider the line AA, so this is the line. So, with respect to line AA, this problem is symmetric problem, am I right. So, if you consider the left side of the dam, I mean cofferdam, or the right side of the cofferdam, you will be getting the same amount of flow, because I mean if you consider the right side of the cofferdam, so flow will be happening in this direction. Okay. If you consider the left side of the cofferdam, so flow will be happening in this direction. So, any one side if you consider, and if you can find out the seepage flow, then that will basically serve your purpose. Okay. So, now let us solve this problem. It can be seen, as I told you, that the flow net is symmetrical about line A. The flow on either side of AA remains confined to that side. Okay. So, that means no cross flow is happening across the line or the plane AA. Okay. So, in the flow net, what is your NF? What is your NF? So, number of say flow channels. So, if you consider left of the cofferdam, that means I am considering this side of the cofferdam. So, how many flow channels are there? So, if you count, so basically you can find out how many flow channels you will be having, right. So, if you look at this flow net, you will be having 6 number of flow channels, right. NF equal to 6, 3 on either side. So, total number of flow channels will be 6, okay. And number of potential drops will be 11 if you see. So, total number of potential drops is 11. So, total head loss is equal to H is equal to how much? 3.3 meter. If you see, that is a difference between the upstream side water top water level to the downstream side top water level. So, in the downstream side means within the coffer dam itself, am I right. So, downstream side means within the coffer dam itself. In the coffer dam itself, you do not have any water level, because you want some dry working condition. Okay. So, H is nothing but 3.3 meter as shown in the problem itself. So, therefore, we can calculate Q is equal to K into H N F by N D, which is equal to 3 into 10 to the power minus 3 into 10 to the power minus 2 into 3.3 meter into 6 by 11 meter cube per second per meter width of the coffer dam. So, that gives me 5.4 into 10 to the power minus 5 meter cube per second per meter width, which is equal to 0.19 meter cube per hour per meter. So, which means the pumping will have to be done at this rate. To keep the excavation free from water. That means, if you want to have some dry working condition inside the coffer dam, so that means if you do not allow any water level in the downstream side, basically you need to pump the water from the coffer dam at this rate, that is 0.19 meter cube per hour per meter width of the coffer dam. Okay. So, I will stop here. So, this is these 4 problems, 4 numerical problems we have considered from the seepage analysis. Now, we will see we will discuss about the next topic, that is consolidation or the fundamental of consolidation. So, now we will consider another very important chapter in soil mechanics, that is fundamental of consolidation. So, when a saturated compressible clay layer is subjected to a stress increase, elastic settlement occurs immediately, right. So, you have some saturated compressible clay layer, and on top of that you are increasing the stress, that means you are applying some load, and because of that you will be getting immediately you will be getting some elastic settlement. Okay. Now, because the hydraulic, so at that time, so nothing is happening. So, you are applying the